This presentation is hopefully review. Now, maybe you haven't had a plant science or soil science or some other science talking about pH, but most people, by the time they get to a class like this, you've had some discussion of pH before. If you haven't, well, I'll go over this to make sure you know what you need to know for this class. If you have had it before, this will be hopefully a great refresher that you will just polish up what you do know about pH. And pH is important from two standpoints. We've talked a lot about grapes in terms of production out in the vineyard, and we've also talked about it in the winery. And pH is important in the wine as well as in the soil in the field, as well as the pre-harvest analysis and the developmental analysis of the grapes as they mature and get ready for harvest. So pH is very important in the soil. It impacts the plant's ability to uptake nutrients. And it's certainly, as I mentioned, important in harvest estimates and wine production. So let's start by talking about an atom. Atoms are made up of three main components. And yes, you can dig down inside of these components to get even further components like quarks and gluons and what have you. But at the most basic level, atoms that make up everything are made of three components: protons, neutrons, and electrons, with the protons and neutrons making up the relatively large components of the nucleus. Protons and neutrons are extremely small, but comparison to electrons, they're large. And they make up all atoms. The simplest of all atoms is just a hydrogen atom, which has one proton in the nucleus and one electron orbiting. And you'll notice that the proton has a plus sign. It's a positively charged subatomic particle, and the electron has an equal size negative charge. So a hydrogen atom is neutral. One positive charge, one negative charge. They balance each other out, so it's a neutral atom. Now, hydrogen doesn't exist this way in nature. There is no hydrogens with one proton, one electron. It's extremely it's extremely reactive and unstable in this form. So it will react with something. And so the hydrogen atom is part of other molecules, or possibly two hydrogens together, H2. They're stable if two of them are together, although that also is very reactive. We burn hydrogen gas to get rocket ships into space. Hydrogen is very reactive and volatile. But anyway, that is a hydrogen atom. A much larger atom is the carbon atom. This is a carbon-12 atom because it has 6 protons and 6 neutrons in its nucleus. So a total of 6 positive charges, and therefore there are 6 electrons or 6 negative charges orbiting it. Carbon is also very reactive and very flexible in the way it reacts. And so carbon is the perfect building block for life. We are carbon-based life forms here on Earth. Plants, animals, bacteria, everything we know of that we call life here on Earth is based on carbon chains, carbon chemistry, which makes up all of the carbohydrates and nucleic acids and proteins and fats that make up living things. So that's an atom, and we can put atoms together into molecules. And this is one molecule that I hope you're aware of, H2O, water. H2, 2 hydrogens, and you can see those 2 hydrogens, and O, oxygen. 2 hydrogens plus an oxygen in a molecule like this is water. And you'll notice that it is not in a line. It isn't HOH with the hydrogens coming off equally on either side. They're at an angle. And because of that angle, water is considered polar. And that's not important for the pH discussion necessarily, but it is important in water relations and all kinds of things, even life on Earth. Water being polar is very important. Why do we call it polar? Because oxygen has 8 positive charges in its nucleus, 8 protons. And there's only 1 proton in each of these hydrogens. So when the electrons are orbiting water, the electrons are pulled a little bit stronger towards the oxygen side. And so you get a little bit of an excess of electrons over here at any given moment, and a little bit of a reduced presence of the electrons on this side, because the hydrogens don't pull as hard. Because of that, you're exposing the positive charge on these hydrogens a little bit, so it's positively charged just a little bit, polar or partial positive charge on the hydrogen side. And because of these extra electrons, or a little bit of extra electron presence on this side, you get a little bit of a partial negative charge. Now, a water molecule is very stable in this form, and it is reactive as well. It is involved in all sorts of chemistry, including the chemistry of respiration when we burn sugars in our cells, or photosynthesis. Water is used all the time. It's broken up for its parts, but it's still a pretty stable molecule. It's not highly reactive, even though it is involved in a lot of chemistry. But it's not perfectly stable, and water can actually split. And one of these hydrogens can split away, leaving an OH, or hydroxide. But when that happens, when the hydrogen separates from water, leaving behind a hydroxide, it doesn't take the electron with it. It escapes as just a proton. A free proton escapes a water molecule, and it's positively charged. It's a proton. So you have H+, a positively charged proton is called a hydrogen ion. And what's left is a negatively charged hydroxide ion, OH. So here you can see that in a chemical reaction equation. Now, the favored direction of this reaction, the more stable direction of this reaction, is when a hydroxide ion with all 10 of the electrons bumps into a hydrogen ion with 0 electrons. They form water. So you can see here's a bold arrow pointing to the left. But because there are trillions of trillions of trillions of water molecules, even in a glass of water, the percentage might be very low, but the probability is extremely high that some of them have ionized or broken apart at any given time into hydroxide and hydrogen. And if I have truly pure water, laboratory grade pure water, it is considered neutral because I have a balance between the hydrogen ions and the hydroxide ions. I have equal numbers of both in pure water. And it is the hydrogen and hydroxide ions that are key to understanding pH. But it's not just water that can ionize. It is something that's easy to illustrate, easy to describe, as I show in the equation on the screen right now. But there are many things that we call acids or bases that can come apart in a water solution and ionize in this way. So, with that background, what is pH? pH literally stands for potential hydrogen. And the word potential is important, but unless you're in an advanced chemistry class, I've rarely seen anybody bother to get into the details of hydrogen ion activity and the potential of hydrogen, which is the effective hydrogen ion concentration, how much hydrogen is there. But because it's a little more complicated than that, we don't just call it the hydrogen ion concentration, we call it the effective hydrogen ion concentration, or the potential hydrogen, pH. Again, it's a simple concept that some students learn in grade school. They talk about pH, and then you find out sometimes in grad school that, wow, this stuff is a lot more complicated than I realized, which is true of damn near anything you might study. But it's the potential hydrogen. And we can express that in an equation. The pH, or potential hydrogen, equals the negative log to the base 10 of the hydrogen ion concentration. Now, what the hell is the square brackets? Square brackets in chemistry can be directly translated into English, meaning the concentration of, period. The concentration of. So if I see a chemical substance inside of square brackets, I'm saying the concentration of that substance. And H plus is hydrogen ions, or free protons. So what is the log? A log is nothing more than an exponential or geometric scale. So let me give you an example of an exponential scale. Let's say I have a bacterial growth. I start with 1 bacterium. After one life cycle, I have 2. Then I have 4. Then I have 8. Then I have 16, then I have 32, 64, 128, 256, on and on. It doubles each time. That's an exponential growth. And to represent exponential growth, it is often more understandable, easier, and a more accurate representation to use a logarithm. Now, a logarithm to represent bacterial doubling would be base 2, a log base 2, because it's doubling each time. A log base 10 increases 10 times each step. So let me give you another example. We're here in California, the wonderful land of earthquakes. We know about the Richter scale. A Richter scale magnitude 1 earthquake, you probably can't even feel. A magnitude 2, if you're in the right spot, you might have gone, what was that? Did I feel something? Was that an earthquake? But most people say, I didn't feel anything. But it's 10 times more energy than a 1. A 3 is 100 times more energy than a 1, or 10 times more energy than a 2. So at a 3, with 100 times more energy than a 1, if you're near it, you're probably going to say, oh, wow, there was an earthquake. I felt it. The ground shook. At a 4, you're definitely going to feel it. At a 5, things might start falling off of shelves. There might be a crack in the wall. And you start getting 6s and 7s, and you start worrying, is anybody hurt? Is anybody killed? Did buildings collapse? Because each step you're going 10 times more. A 3 is 100 times a 1. A 4 is 1,000. A 5 is 10,000. A 6 is 100,000. A 7 is 1,000,000 times stronger than a 1. 1,000,000 magnitude 1s going off at the same time in the same instant at the same place. Now, if I'm going to have a scale, a graph, trying to show from a 1 to a million, that's a pretty hard graph paper to make. I can't show it too well, but I can use a logarithmic scale to show you a 1, 2, 3, 4, 5, 6, 7, even an 8, or even a 9 earthquake. They can happen at that size. And I can wrap my head around that. I can understand it. It's something that can be easily communicated. But can I have an earthquake of, 772,609? Yeah, you can have the earthquake. Would I understand what that number means? And the answer is likely no. But you say, oh, I've got a 6 point, what would that be? Somewhere probably around 6.5-ish. Now you can say, oh, 6.5. I kind of know what that is. It's not huge, but that ain't small either. Wow, we had a real earthquake. That something bad could have happened at 6.5, right? That's a logarithmic scale, the Richter scale. In pH, we also have a logarithmic scale. The difference between pH 0 and pH 14, the entire range of the pH scale is 0 to 14. And the distance between these is 10 trillion. 10 trillion. I can't make graph paper with 10 trillion lines. I need to do something with logarithms, with an exponential scale that's going to allow me to write those numbers with a difference of 10 between each one. And I can easily write from 0 to 14. That's easy. And I can even understand 0 to 14. I can communicate it easier than 0 to 10 trillion. So that explains the logarithmic scale. What about this negative? The negative means that they are inversely correlated, meaning that as pH goes up, let me use this hand, as pH goes up, the hydrogen ion concentration goes down. As the hydrogen ion concentration goes up, the pH number goes down. So with a really high hydrogen ion concentration, I have a very low pH. And I'll show you that on a graph in a moment. So what did I just say? The pH scale is logarithmic. A difference of 1 unit represents a 10-fold change in hydrogen ion concentration, or effective hydrogen ion concentration. So here is a scale, the pH scale, with 0 at the top, 14 at the bottom. pH is extremely acidic at pH 0 and gets slightly less acidic as I move to higher numbers. So the acidity is going down as the pH number goes up. So at a pH 1, 2, 3, these are still strong acids, but they're getting progressively less strong acids. 4, 5, and 6, again, I'm getting less and less and less acidic until I reach 7, which is considered neutral. And what is neutral? Human blood is right about pH 7, very close to neutral. And pure water, not natural environmental water, not rainwater, not lake water, pure water. And pure water can only be made with a little human intervention, with a laboratory purification process. And if you truly have pure water with nothing else in it, it's neutral, pH 7. And I showed you the equation of that earlier. But you notice here, normal rainwater is slightly acidic, pH 5 point something. Why is natural sweet water, fresh water, acidic? Well, it's acidic because of gases like carbon dioxide in the air and other gases in the atmosphere get into the water. Even if it's a raindrop up in the clouds, the raindrop has dissolved oxygen and carbon dioxide and other things in it. It's not pure water, even in a cloud. There's no salts in it. Well, very little. There could be some salts from dust in the atmosphere, but very little. But there are dissolved gases in raindrops and in rivers and lakes. And what happens when you dissolve some gases, like carbon dioxide? A little bit of carbon dioxide dissolved in water becomes carbonic acid and bicarbonate. And when it goes to carbonic acid to bicarbonate, it's releasing hydrogen ions. What are hydrogen ions? Free protons that cause acidity. They cause the pH to go down. The more hydrogen ions, the more the pH goes down. So I have rainwater with a lower number than pure water. The pH is lower. All right. What about these numbers on the side, the hydrogen ion concentration? 10 to the 0 power at pH 0. What is any number to the 0 power? Any number to the 0 power equals 1. So this is a concentration of 1, or pure hydrochloric acid, pure hydrogen ion concentration. Now, it's not pure hydrogen ions. It has to be a water solution. So it's not technically pure hydrogen ions. It is just the most concentrated hydrogen ion water solution that you can make, pure hydrochloric acid, or saturated, I should say, saturated hydrochloric acid. That is the lowest pH you can get, the most concentrated hydrogen ions you can get. So we call that 1, the starting place. And as we dilute that pure hydrochloric acid, if we dilute it 10 times, or 1/10, we end up with pH 1. 1/10 is pH 1. And you say, that doesn't say 1/10, that says 10 to the minus 1, 10 to the negative 1 power. Well, literally 10 to the negative 1 is exactly the same as writing 1/10. 10 to the negative 2 is exactly the same as 1/100th. 10 to the negative 3 is exactly the same as saying 1/1000th. All the way down to 10 to the negative 14, which is 1 over 10 trillion, 1/10 trillionth. That's a very low hydrogen ion concentration, 1/10 trillionth. And how do I get that low? Saturated sodium hydroxide solution. Saturated sodium hydroxide is a water solution that contains nothing but sodium ions, the positively charged ions, and hydroxide ions. And the chance of a hydrogen ion surviving in that environment is virtually non-existent. If a hydrogen ion does somehow appear in that solution, it's going to immediately bump into a hydroxide ion and turn into water, and it's gone out of the solution. It didn't disappear, it just turned into water. It's no longer acidic. Okay? So that's what these hydrogen ion concentration numbers mean. At very, very high hydrogen ion concentrations, we have an acidic solution with a low pH number, 1, 2, 3, 4. And things that we're familiar with in the 2 range, we have stomach acid, very acidic in our stomachs. 2 point something, we have lemon juice, also very acidic. Other common drinks, vinegar, cola and beer, or I should say liquids, but vinegar, cola, and beer. Tomatoes in the 3 to 4, 4.5 range. Coffee, rainwater, urine, and saliva in the 6, 6.5 range. And then we get to the other side. After neutral, if we go to a number above pH of 7, when we get into the 8, 9, 10 through 14, we call those basic solutions or alkaline solutions. And in the basic or alkaline solutions, we have things that we might be familiar with, like seawater, slightly alkaline, baking soda, household bleach or ammonia, oven cleaner. Now, a lot of these things are potentially toxic, and some are not. Baking soda, milk of magnesia. If you have an upset, sour stomach, milk of magnesia is something you would drink to calm down a sour stomach. What is a sour stomach? Too much acid. Maybe you have heartburn. And milk of magnesia is just a product you can drink to neutralize the acid by drinking a food-safe base. So, I'm going to take a break. Be right back.